This problem is from First Law of Thermodynamics. Problem says 1 mole of a monatomic ideal gas undergoes the cyclic process JKLMZ as shown in the PT diagram. So we have a PT diagram. On the y-axis we have pressure and on the x-axis we have temperature. And this is the cyclic process J to K, K to L, L to M and M to Z. Different temperatures are given and different pressures are also given. Then we have to match the quantities mentioned in list 1 with their values in list 2 and choose the correct option. The gas constant R is also given. So this is the list 1 and this is the list 2. So this list 1 basically is related to work done, change in internal energy, heat or total work done. So what we will do is, we will analyze each path separately and I will calculate change in internal energy and work done for each process, and subsequently we can calculate change in heat. So let us first consider what are the things that is given. So we have been given this is a 1 mole of gas and this is the ideal gas, so we can apply PV equals to nRT, and it is also given this is a monatomic gas. This means CV equals to 3 by 2R. Now let us consider process M to Z. In this process temperature is constant and temperature is basically T naught. Such kind of process is called isothermal process. And in case of isothermal process, work done is given by this formula, that is nRT log Vf by Vi. Since temperature is constant, we can also write P1 V1 equals to P2 V2, that is Pi Vi equals to Pf Vf. So I can rewrite this expression like this. So Vf by Vi becomes Pi by Pf. So this is work done. Now what is the initial pressure? So this is from M to Z. So initial pressure is 2 P naught. So let us plug this value 2 P naught. And what is final pressure? Final pressure is P naught. So this becomes ln2. And number of mole is 1. So we can write this is 1 times R times T naught, because temperature for this process is T naught. So this is simply R T naught ln2. What is the change in internal energy for this process? Because temperature is constant, so delta T equals to 0, this means NCV dt equals to 0, this means change in internal energy for this process is equals to 0. So this is for option S, that was asked what is change in internal energy for gas in process MJ. So in process MJ, change in internal energy is equals to 0. Now let us consider process J to K. In this case pressure is constant, that is why this is a isobaric process. Now in case of isobaric process, the work done is given by P times dV, and dV is Vf minus Vi. Because pressure is constant, when I am integrating P dV, I can take P outside and integral of dV will be Vf minus Vi. And PV can also be written as nRT, PV equals to nRT, that is ideal gas equation. So P times Vf will be nR times Tf, P times Vi will be nR times Ti, and I can take nR outside. Now let us plug the value. What is the final temperature? Final temperature is 3 T naught. And what is initial temperature? T naught. And number of mole is 1, so this becomes 2 times R times T naught. So that is 2R T naught. So this is the work done in this process. What is change in internal energy? That is dU. So that is N CV dt. N equals to 1, that is given, and for monatomic gas CV equals to 3 by 2R, and change in temperature is 3 T naught minus T naught, that is 2 T naught. So this 2 and this 2 cancels out, so this becomes 3R T naught. So the option Q was change in internal energy of the gas in process JK. So we have calculated change in internal energy for process JK. Now let us consider K to L. This is an isothermal process because temperature is constant. Once again, work done in isothermal process is nRT log Pi by Pf. We have already shown this in the first part, that is in this process. Now let us plug all the value. So this is R and temperature in this case is 3 T naught and number of mole is 1 and final pressure is, initial pressure is P naught and final pressure is 2 P naught. So this is P naught and this is 2 P naught. So this becomes ln 1 by 2 and ln 1 by 2 can also be written as minus ln 2. So this is minus ln 2 times 3 T naught times R. So this becomes minus 3 R T naught ln 2. And what is change in internal energy for this process? So change in internal energy is 0 because temperature is constant. We have to also find delta Q, that is change in heat in this process, that is one of the option. So we can use first law of thermodynamics, that is dQ equals to du plus dW, or you can say W. So du is 0 and W is minus 3 R T naught ln 2. So dQ equals to minus 3 R T naught log 2. So that was option R, heat given to gas in process KL. So this is the heat. Basically this heat is ejected because we have a minus sign. But we have to write the answer, so we can basically put in terms of minus sign. So that will be minus 3 R T naught ln 2. The final process, that is L to M. Once again pressure is constant, so this is a isobaric process. And work done is PdV. Pressure is constant, so this becomes P Vf minus Vi, and if I use ideal gas equation, that is PV equals to nRT, so this can be written as nR T naught minus 3 T naught, because here you have, that is final temperature, that will be nR Tf minus Ti, final temperature is T naught and initial temperature is 3 T naught. So this is simply minus 2 T naught R. What is change in internal energy in this process? That is N CV dt. That is 1 times 3 by 2R and delta T is minus 2 T naught. So this 2 and this 2 cancels out. So this becomes minus 3 R T naught. So finally we have to also calculate work done in the complete process. That was option P. So we have calculated work done in each path and then we can sum. This is first path, second, third and fourth. So if I sum all these work done, so this becomes minus 2R T naught log 2. So now we have calculated all the options and you can match and you can find the correct answer. So I hope you like this video, and if you like my videos, please share with your friends, like on my channel and subscribe to my channel. I will see you in the next video. Thank you.